Let's discuss some important numericals on photoelectric effect. The formula that we will be using in the numericals will be the change in potential energy will be equal to the charge multiplied by the change in the potential. Let's solve first question. Question 1. It says that there is one alpha particle. This alpha particle is at 10 volt and at this potential it has 30 electrovolt kinetic energy. Now afterwards its energy changes to 0 electron volt. You have to find out that what is the potential at this energy. So let us solve this question. So first of all, we will put the value of change in potential energy, that is 30 minus 0 equal to, and the alpha particle charge is plus 2, so we are writing that, and then here x minus 10. Now here we are putting the values, so 30 equal to plus 2 x minus 20. So 30 plus 20 equal to 2x. So it will be 50 equal to 2x and x will be equal to 25. So here the value of x will be equal to 25 volt. If you are asked what is the change in potential, so your answer turns out to be the final potential minus initial potential, which will give you the answer, that is 15 volt. This is the change in potential. Now let's discuss some important common misconceptions that often we make during the photoelectric effect studying. So the first common misconception that we generally make is that if any electron requires 10 electrovolt as its work function, so we might think that if we provide two photons which are of 5 electrovolt each to this surface, then we are able to eject the electron, but that is not possible. Here we have to provide one photon at least which should have the equivalent energy, that is minimum energy should be 10 electrovolt. The second is that if two photons are there which are of 14 electrovolt, if two photons are there which are of 14 electrovolt and there are two electrons each of the work function of 10 electrovolt, then the two electrons will be ejected and each of them will be having kinetic energy equal to 4 electrovolt, as 10 was consumed during the work function and remaining was 4, which is made as their kinetic energy. Similarly, if I say that if I have two photons, if I have two electrons that each have the work function of, each with the work function of 10 electrovolt, then I cannot use a photon, a larger photon which will be having the 20 electrovolt as its energy to emit it. So we cannot use this. What it will do, rather it will emit one electron with 10 electrovolt, which is the remaining as its kinetic energy. When we plotted the graph which was against the stopping potential and the frequency, we obtained a linearly straight line. This straight line is constant for various other metals, because suppose this axis is y axis and this axis is x axis. So if I divide y upon x, I get the work function upon frequency. Now if this work function or this if this potential, stopping potential, and these frequency both are multiplied by Planck's constant and charge q, and this frequency is also multiplied by Planck's constant and charge q, so what happens is that this potential into charge, this becomes the energy. So this we can write as, there are two forms of energy. The first is that energy equal to potential into charge, and the second form of energy is energy equal to frequency into h, which you already know, this is h nu. So what I will do over here is that I will substitute the value, and here I get, at the above equation I get E multiplied by h, and in the lower equation I will get E multiplied by q, which will be equal to potential upon the frequency. Now these two energies get cancelled and we get h upon q. Now this h is Planck's constant, which is a constant, and we are talking about the electrons. So these electrons have a constant charge that is 1.6 into 10 to the power minus 19 coulomb. So we can say that this Planck's constant as well as this charge, both of them are constant, and therefore we can say that any graph for various other metals also, this graph is constant. This graph is constant because we found out that both of the above numerator and the lower denominator are constants. So this graph slope, this especially when we talk about this slope, so we find out that this slope is constant for the various other metals also. Now let's see the question. The question says that if the work function of the metal is 6 electrovolt and we provide the energy of 8 electrovolt, then what will be the kinetic energy of the emitted electron? So here the work function of the metal is already given as 6 electrovolt and the energy which we provide is given as 8 electrovolt. So we already know that if we are providing extra energy, so the kinetic energy of this electron will be 8 minus 6, which is equals to 2 electrovolt. So here one equation comes that kinetic energy equal to energy which we give minus work function, or energy minus h nu naught. This will be equal to kinetic energy, and this can be further equalized as half of mv square. Now if the question also asks that what is the stopping potential required, so as the kinetic energy of 2 electrovolt the electron is having, so in order to stop we should provide the stopping potential of minus 2 electrovolt, just opposite in sign but equal in. See the next question. It says that the work function of a certain metal is 3 electron volt and we provide the kinetic energy of 8 electron volt, then what is the velocity of the electron? So first of all let us calculate the remaining energy that we have to calculate. This energy will be equal to the kinetic energy that we have to calculate equal to the energy that we provide minus the work function. So it will be equal to 8 minus 3, which will be equal to 5 electron volt. Now put this in the equation that Ke equal to half of mv square. So when we have to find the answer of velocity, we will put the value of Ke, that is 5, and this 2 will go over there multiplied by 2 upon the electron mass is 9.1 into 10 to the power minus 31 kg, and this velocity is in square, so we will underroot it. We will get the velocity of the emitted electron. In the next question, if it is given that we have a metal and on this a frequency of suppose nu is provided, this metal has the work function as W naught and the kinetic energy of the emitted electron is E. Now if the question says that now the frequency nu is twice of original frequency that we provided earlier, now what will be its kinetic energy? So first of all we will be writing the equation. So equation 1 was E equal to h nu. This is kinetic energy equal to h nu minus w0 or w naught, that is a work function. And now afterwards it says that kinetic energy nu, which we can write as Ke dash, equal to twice of h nu, because this frequency is double now, minus the work function which is remaining the constant. Now this is our equation 2 and this is our equation 1. Afterwards, now when we put this equation, when we put the value of this in the equation second, we come to know that twice of h nu minus E, which is the value of this work function, if we send it over here, will be equal to E Ke. Now afterwards we see that h nu plus E equal to h nu plus Ke equal to Ke dash, and now this will be equal to work function plus twice of kinetic energy. Means if we are doubling the frequency, the kinetic energy will not double, actually it will more than it will double, it will become more than double.